Okay, let's dive right into this explainer. Welcome back. Today we're focusing on one of the most fundamental and honestly fascinating events in all of chemistry, how multiple chemical reactants actively merge together to create something entirely new. Specifically, we're looking at type 1 of the essential chemical reactions, which is known simply as the combination reaction. And we're really going to hone in on exactly how combination reactions form products.
But before we throw some scientific formulas your way, let me just ask you a quick question. What do whitewashing a wall, burning a lump of coal in a furnace, and creating the very water we drink all have in common? Seriously, think about it for a second. They seem like completely unrelated events, right? One is construction, one's energy generation, and one is literally the basis for life itself. But chemically speaking, they are bound together tightly by the exact same underlying thread.
Let's move to Section 1, the core definition, the rule of the single product.
So, to understand what that underlying thread is, we've got to look at the foundational rule of the chemistry we're exploring today. A combination reaction occurs when two or more reactants combine to form a single product. I really want to deliberately emphasize that for you. A single product. It actually doesn't matter if you start with 2, 3, or even 4 completely different chemicals. The defining characteristic of this entire reaction type is that ultimate two become one dynamic. All of the starting materials merge to form one singular outcome. Think of it kind of like baking a cake. You have distinct, separate ingredients on the left side of the equation, represented here by our two icons, and they physically merge into one unified product on the right. That is the pure essence of how combination reactions form products. They synthesize, they combine. Boom, one new thing.
Moving right along to Section 2, real-world chemical examples, from whitewashing to water.
Now that we've got that abstract rule locked in our minds, let's bring it into the real world and see how this simple equation applies to everyday stuff happening all around us. Looking at our first row, we have solid calcium oxide, that's CaO, plus liquid water, H2O. These combine to form CaOH2, which is an aqueous solution of slaked lime. In practical, everyday terms, that is the exact chemical process used for whitewashing walls. Next down, grab some solid carbon, C, and let it react with oxygen gas, O2. They yield a single product, CO2, or carbon dioxide gas. That is the combination reaction happening every single time you are burning coal on a grill. And finally, 2 molecules of hydrogen gas, H2, plus oxygen gas, O2, yield 2 molecules of H2O, liquid water. Yep, making water itself is a combination reaction.
Let's isolate that first example for just a second, because it's incredibly common. We start with quicklime, which is that dry calcium oxide, and we add water. These two distinct reactants aggressively merge to form slaked lime. By understanding how these combination reactions form products, we understand exactly how we physically create the vital material used by builders and painters to whitewash and protect walls all over the world. It's chemistry in action.
All right, Section 3, the combustion connection. A high-order thinking puzzle.
Okay, so we've got the basics down beautifully, but chemistry always loves to throw us a curveball to keep us on our toes, right? It's time to challenge our critical thinking and move beyond basic memorization. Here is a classic higher-order thinking skills prompt from the CBSE curriculum. Is combustion always a combination reaction? Just take a second and really think about that, keeping our coal and water examples in mind. Well, here is the solution to the puzzle, and it's a vital distinction to make. Yes, combustion is always a combination reaction. When you burn coal, the carbon combines with oxygen to form that single product, carbon dioxide. However, and this is the really tricky part, a combination reaction is not always combustion. Remember our water example? Hydrogen and oxygen combining to make water is absolutely a combination reaction because two things become one, but it definitely does not involve burning or combustion. So the crucial takeaway is this key rule. Most combination reactions are exothermic. That just means they release energy, usually in the form of heat, as a byproduct of the reaction. Think back to our examples. You'd certainly feel the heat radiating from burning coal. And, perhaps surprisingly to some, if you mix quicklime with water, the container itself gets incredibly hot as the slaked lime forms. The very act of those reactants merging into a single product releases a huge amount of pent-up energy. Which brings us to Section 4. What comes next? Flipping the equation. We've seen how two or more things combine to become one, how that amazing process releases energy, and how it forms the materials that literally make up the world around us. But, as we know, every rule in chemistry seems to have a mirror image, Which brings us to a final, provocative thought to wrap up today's explainer. What happens when you do the exact opposite? If a combination reaction is multiple reactants merging into a single product, what do we call it when a single reactant actively breaks apart into multiple products? Well, that destructive process is called decomposition. But to see exactly how that reverse chemistry works, you'll just have to join me in our next explainer. Until then, keep looking at the world around you and asking how things are put together.